So let's now finish up about, so we've discussed now in the in-spiral, we can use love numbers, either the tidal love numbers or the spin-induced ones to test the nature of the object. In the ring down, it gets also interesting because, so in the in-spiral, of course, we test the nature of the progenitor individual objects. In the ring down, we test the nature of the final remnant. Yeah, I also want to mention for black hole perturbations, there's a big open source database, also with Mathematica notebooks and Python notebooks and so on, the black hole perturbation toolkit, where you can find many codes if you want to use them. So, okay, this is almost too easy, so I will skip it. So, one interesting thing, you want to see it?
No. You're in charge here.
Yes, so this is just to remind you again of this no-hair property of black holes that, okay, it's not, it's more still a conjecture for astrophysical black holes. That's also that related a bit to should have singularities only inside the horizons. But basically, we know at the merger, the configuration that forms is a very highly dynamical object. Well, one cannot even say object, region of space-time, let's say. And at the end, it should go down to a final equilibrium black hole with no hair. So in the process, somehow it has to lose its hair. It's also not so clear when after the merger you can consider the system as a perturbed remnant. That is also in the community still a big debate. But, you know, sometime after the merger, okay, you can think of it as a perturbed final black hole. And of course, it's interesting that black holes can even vibrate and have these modes in some sense because there's no matter. It's really space-time. Of course, nowadays we're used to dynamical spacetimes and all of this, but in the beginning, when people were studying black holes, they kind of thought of them as really just eternal static objects. And then when people discovered, oh, they actually can have these vibrations or their space-time, then it was a big revelation and kind of a new aspect. So to describe this, again, we go to these black hole perturbations that we had before. Actually, an interesting feature is that the even and odd sectors will turn out to have the same quasi-normal modes. So it's actually easier to work with the odd sector because there are only two functions. But since we already set up everything for the even, I also continued with the even here. So again, you find after keeping the frequency dependence in the field equations that you can write down a master equation for some variable z now, which is a combination of two of the perturbation functions. And it looks very nice, like a Schrödinger equation, except it comes at the cost of having two radial variables. One is the tortoise coordinate, r star, and one is just the normal r. But okay, we know also how to convert between them. And this potential is, some potential that depends on the mass and the L spherical harmonic number. So at this point, it's not so insightful, but we can plot the potential and kind of get also its asymptotics. And we see close to the horizon, it falls off kind of, or the perturbations fall off in this way, whereas at infinity, it has a different asymptotic behavior. And we also see the peak of this potential is quite near the light ring, which is 3m. So now we actually work in units where G and C is 1 because we are in the strong field limit here. So that's quite interesting. And actually, as the L number gets even higher, the peak moves closer and closer to r equals 3m, and the potential becomes steeper and steeper. So then, for now, as we already said, to compute gravitational quasi-normal modes, you have to solve this equation, but with certain boundary conditions, namely only ingoing waves at the horizon and only outgoing waves at infinity. And this turned it into an eigenvalue problem. where there's an infinite set of complex frequencies that are solutions to this equation with the boundary conditions. And these infinite sets of complex frequencies, they are characterized by three numbers. So again, we have the spherical harmonic numbers, L and M. Actually, for Schwarzschild, the M doesn't matter. But for, and then there's this radial overtone number, N, which is also interesting. Let me just check. So as I mentioned, it turns out the even and odd perturbations, they can both be written in this form with the potential of some master equation with the potential, except the z variable in both cases is different, differently related to the metric perturbations, and the potential is different. But nevertheless, magically, at least for black holes in GR, the even and odd sectors give the same quasi-normal mode frequencies. For black holes in modified gravity, that's usually no longer the case. But what we can do to get a bit of intuition about these frequencies is to consider the geometric optics or iconal limit and see if we can get some insights. So one thing I have to tell you is if you series expand this earlier potential that we had here, now for large L, you actually get a simpler form. So yeah, it's actually written down there. For L goes to infinity, you get a term proportional to L squared, and then 1 to order L, and then L to the 0. And let's see if we can do an iconal approximation, some insight. So that is the limit of large L. So we make an ansatz like you would usually do. It's some amplitude as a function of R star, and then this phase, which is rapidly varying, to the IS of R star divided by epsilon, where epsilon, so epsilon is much less than 1, and we also work in the limit 1 over L is much less. And then substituting this into the master equation, which, okay, now we lost it, but you remember it was this Schrödinger-like equation, then we get something like, or maybe actually considering the time, I might not go through this in detail, but I leave you as homework for next time, yeah, to substitute this and find what is the frequency in the iconal limit. So you will also find, that epsilon is proportional to 1 over L. So it basically means this kind of wave packet you consider has the same extent in the radial as in the angular directions. And you also find omega is proportional to L. And no, yeah, not also, but you also find omega LM is proportional to, like you get that result, L divided by 3 square root of 3M, which is L times omega of the light ring. Which you can work out, yes.
The real or the imaginary component?
Yeah, so if you carry this iconal approximation only to the leading order, you only get the real component, real part. If you go to the next order, you get a correction to the real part and you get the imaginary. Yeah, this is the real part, I would say. Yeah, depending on how you view it. Okay, also your homework is then to go to the next page. Could you also get the damping part? But but it's actually, yeah, it's not a long calculation. You just have to go through it. And yeah, then it's interesting to see also what can we learn from this analogy that now the peak of the potential is near the light ring, and now we've seen that these quasi-normal modes, at least in this geometric optics limit, they also have frequencies L times the frequency of the light ring. Well, so that suggests also an interpretation that, first of all, these long wavelength modes, they kind of, they are produced by maybe by the near the black hole, but they cannot go out to infinity immediately because they're stuck at the potential barrier. So they linger actually near the peak of the barrier, and then over time, different components dephase a little bit. So short wavelength modes can build up and then leak out to infinity. So it means basically that these quasi-normal modes, they have properties due to the filtering of the barrier, or here, which is more like the peak of the potential. I mean, it's a bit of a coincidence that it coincides with the light ring, but nevertheless, but again, this potential depends on properties of the black hole, like the mass. So in the end, we do probe the black hole. And from this analogy with the light ring, actually, you can get very nice results. So we already saw for the real part of the quasi-normal mode frequency that there seems to be a coincidence, but you can push it a bit further if you consider that, you know, from dynamical systems that near a critical point in the phase space, some universal behavior emerges for if the critical points have the same topologies and so on. So if you then ask, well, if you're for a photon orbit near this light ring, what is the trajectory of particles that could just escape to infinity? Well, that and the rate of that divergence away from the light ring is given by these Lyapunov exponents. And it turns out you can use those to get the imaginary parts of the frequencies also. So if you're curious to read a bit more about all of this, there's a nice article that reviews these kinds of intuitions. All right. Then just to say what we can also conclude, well, we also saw it here already, that the quasi-normal mode frequencies, they scale like all over the mass, at least in this limit. Turns out also if you compute it numerically, they also scale like 1 over the mass for non-spinning black holes. So it means if we have a larger mass black hole, it vibrates at a lower frequency, but it rings for much longer, because you find then this decay constant of the frequency, which we define as 1 over the imaginary part, it's proportional directly to the mass. And for spinning black holes, all of these modes also depend on the spin, but no other parameters because, again, of the no-hair property. And this can be then used, if you measure different modes, you can really test if the final remnant is a no-hair black hole or not. Okay, and then just to wrap up, then how does it get imprinted in the ring down signal? Well, the signal is again the 1 over r part of the waveform at infinity, and it's given by some amplitudes, and then the damped sinusoid from the quasi-normal modes. And the amplitude depends really on the characteristic of the collision. It's just a constant, how much it kind of dictates the content of modes that is excited initially, and then, but then they just decay away and oscillate dictated by the quasi-normal modes, so just dictated by the properties of the black hole itself. And okay, for other objects, the ring down can be very different. So it's clearly a characteristic fingerprint. There was also a detection of a ring down signal that you can see here for GW 190521, which you might have heard of because it was the most massive binary black hole merger detected so far, with really large masses. So 85 and 66 roughly. And there mainly the merger ring down was detected, and indeed you can see qualitatively the signal looked like the expected ring down, and it could be used for further tests. All right, then just to wrap up, are there any more questions about the ring down? Of course, maybe I should also say, we have now done perturbations of non-spinning black holes. When you go to spinning black holes, it gets much more complicated. Then it's common to work with curvature perturbations instead of metric perturbations. And actually, the curvature perturbations can also be related to the metric perturbations at the end, or if one just needs the radiation at infinity, there's some nice relation between a certain curvature scalar and second derivatives of the waveform at infinity. But yeah, that would require a lot more time, so I am skipping all of this. But just to know that there's also a formalism for black hole perturbations with spins.
Can I have a question about this? These plots. So which point are we sure that it's the ring down?
Yeah,
That's
yeah,
there is not much data to fit.
Yes. So that also depends on who you ask. There are some claims by some groups saying if you include enough overtones, you can start the ring down immediately after the merger. Other groups say, no, you have to really wait until maybe 20 m time after the merger or 15 m before you're in the ring down regime. Other groups say, well, you actually have to include nonlinearities, and then you can go a bit closer to the merger. So that is really an active area of research at the moment. So I think you're right, maybe based on the data, one cannot be entirely sure. And also, I mean, if you include many overtones, it means you have many of these amplitudes that you can also try to play with. So you might be fitting too many parameters at that stage to the signal. But okay, I don't know. We have to see what future events tell us about all of this.
Going in somewhat orthogonal direction, but one of the things that I heard is that the asymptotic overtone limit.
Yeah.
And if you look at the real part of the quasi-normal mode,
Yes.
then it gives you some information about quantum gravity.
Yes.
And
Hod also has a paper
yeah.
on this. Yes.
So I was wondering if people have considered that limit for black hole mimickers.
Not that I'm aware of. You mean just seeing, is it degenerate with information about quantum gravity, or
Does it have some information about the deformation on the horizon?
okay. Yeah, I don't know of a specific work, but yeah, it could be worth a bit more of an extensive search.
Can the mimickers also reproduce, like mimic the ring down?
Yeah, so that is a big question also. So no one has so far computed a self-consistent model of, ring down in some of these fastball or microstate geometry scenarios. What people have done is computed toy models where they put some reflecting barrier close to the horizon and then saw what's the ring down. But then there's also a question, is this stable? Because you put some strange stress energy tensor under perturbations. Is it stable? So here you see an example where they put a barrier close to the horizon. So the horizon is at r star minus infinity. So here they put some barrier so that now waves can get trapped between the peak of the potential and this barrier. And then you get what are called echoes in the gravitational waves, which are, you see kind of the normal ring down signal, let's say. But then a bit later, some of these trapped waves have built up enough shortwave components to escape to infinity. You get a burst of this, an echo of the ring down, and then later on more come out. And the timescales depend, of course, on the features of this modification. So this also, I think there are ongoing searches in LIGO, Virgo, Kegra to look for these echoes. Yeah, I think there have been some claims that some kinds of artifacts were seen similar to this echo, but yeah, I think there's not a conclusive consensus that these have really been observed so far. So again, we need more data, more accurate data in the future to make a concrete statement.
But it's like just a toy model or represent
Yes.
some type of it, something.
No, it's just a toy model. Yeah, you can compute it, for example, for boson stars, which, again, you find, some different ring down compared to black holes. I don't know if you can see it. I think the dash curves here are for black holes or something. I don't remember, but you can clearly see they can be different depending on what kind of boson star you consider. And boson stars, the nice thing is you can also, depending on what kind of self-interaction you put between the bosons, they can become very compact and kind of also a little bit mimic a black hole mimicker, let's say. But I don't remember what kind of boson stars were used here.
But do they have this barrier as the time model, the puzzle?
Yeah, because they have kind of, well, they don't have a real surface, but they have kind of a very sharp drop in the boson density. At a little bit something resembling a surface, but not really. I mean, because it's just a diffuse condensate. Yeah, so they have an interior structure, let's say, also. Okay, I think we are out of time, so let me just say some words of conclusions. Yeah, so we already discussed in the next years, we will have a greater number and diversity of events. And in the next decade, we are really going to need accurate waveforms because we will be totally in a signal-dominated regime, both with ground-based detectors and space-based detectors. And there will be huge numbers of, hundreds of thousands of binaries per year. And some have very high signal-to-noise ratio of several thousands that, we haven't had to deal with yet. Or of course, it offers really exciting opportunities, but then we will be completely limited if we have only current waveforms. So of course, it's really important to improve the waveforms to really take advantage of gravitational waves as new probes for precision physics. So that's my final words.